this we can see the inversion mode of operation of MOS capacitor. So when gate is made more and more positive, what will happen? The increase of depletion layer, depletion region width stop, and more electrons accumulated near this SiSiO2 interface. So in depletion mode of operation, we said there is a depletion region formation, but if we are again increasing this Vg more than this threshold voltage, we know that the channel formation will happen. That means more and more electrons will be accumulated near this surface. So we can see that when Vg is large enough, the surface is inverted. So previously, originally the substrate is p-type substrate, but if you are applied a voltage Vg which is greater than Vt, then this substrate becomes, this surface becomes n-type. So that means p-type is changed to n-type near this surface. That is called inversion. That means inversion happened and p-type is inverted to n-type. So the n-type surface that forms as a result of the applied electric field is the key to transistor operation. So based on the applied gate voltage, the electric field strength will change. That will cause the accumulation of electrons. That is the key of transistor operation. So we can see that to indicate the presence of more and more electrons, band went down strongly near the SiSiO2 interface. That means EC will move more and more closer to EFS to indicate the presence of more and more electrons. So we can say that this Q phi F is, we can see that it is a difference between EI minus EF, but now we can say that this is bulk region. That means this is the surface SiSiO2 interface and this is the bulk region. So we can say that now this EI is, we need to consider only the bulk region minus EF. So that is the inversion region. So we can say that at inversion region, if you are increasing the gate voltage more and more, the inversion happen. That means original p-type substrate is inverted to n-type substrate. So we can say that if you are applied a more positive voltage at the metal, that will be compensated by more negative voltage in this SiSiO2 interface. So this band, we can also see that we can also see that the band bend near the surface, the band bent down more strongly as the substrate near the SiSiO2 interface become more negative. So we can say that sufficiently large positive voltage can bend EI below EF. We can see in figure. Now near the surface EI, this is EI and EI is below this EF, and we can say that the region near the SiSiO2 interface will now have the properties of n-type semiconductor, and the region, this region of electrons that is created by inverting p-type substrate by applying a sufficient potential at the gate terminal is called inversion layer. So we can see that this region of operation is the weak inversion region. So this is the inversion for p-type and n-type substrate. So we said what is the condition for p-type substrate. So when V is greater than 0, accumulation of electrons will happen. So the region of this SiSiO2 interface is inverted as n-type. Actually the substrate is p-type, and for n-type substrate we need a voltage V less than 0, and if V less than 0, accumulation of holes happens near this SiSiO2 interface. That means the n-type substrate is inverted as p-type near this SiSiO2 interface. So this way we can define the inversion in p-type and n-type substrate. Next we can see what is strong inversion. So if we are increasing the gate voltage more and more, the sufficiently strong channel will be formed. That means when we are applied a voltage which is greater than the threshold voltage, the channel will form. So now if we are increasing again and again this gate voltage, the channel strength will increase, and at a particular point this EI bent down EF by an energy level Q phi F. That means this difference, now this EI is below EF by Q phi F. So that condition is called as strong inversion, and the voltage required for that strong inversion is called as threshold voltage in case of MOS, ideal MOS capacitors. So we can say that the threshold voltage is the sufficiently strong channel formed when EI bent down EF by an energy Q phi F. That means number of electrons in the surface. This is SiO2 surface. So now the number of electrons in the surface is equal to the number of holes in the bulk. So that is this number of holes in this p-type substrate is equal to number of electrons in this SiSiO2 near this SiSiO2 interface. That means this condition, that means that condition is called as strong inversion, and the condition for strong inversion is phi s should be, the metal work function should be equal to 2 times phi f. So that is the condition for strong inversion. So we can say that Q phi fs now is equal to the difference between EI and EFS in the bulk minus the difference between EF and EI in the surface. That is Q phi s, that is called surface potential. So we can say that the surface potential is the potential difference across the depletion layer and is defined as the difference between the Fermi potential in the bulk semiconductor minus Fermi that is the difference in the Fermi potential in the bulk semiconductor and the Fermi potential in the surface, that is at the SiSiO2 interface. This surface potential is defined as the EFI at the bulk minus the Fermi potential at the surface. So that is a surface potential. So we can see that phi s is equal to EFI bulk minus EFI surface divided by Q. So the surface potential, we can say that this depend on the voltage applied on the gate. As the gate voltage increases, the band bend more and the surface potential will increase. So we can say that the threshold potential for an ideal case, for an ideal MOS capacitor is defined as the voltage at which strong inversion happens. So we can say that the surface is inverted whenever phi s is larger than phi f, but a true n-type conducting channel is formed when phi f is equal to 2 phi f. So that is the condition for a true n-channel formation. So this is called strong inversion. So we can see that at strong inversion, the phi s condition is phi s equal to 2 phi f, and the voltage required for the strong inversion is defined as the threshold voltage, and this phi s should be equal to 2 kT by Q log of Na by Ni, or we can also write Q phi f is equal to kT by Q log of Na by Ni. And this, what are the information, physical information we will get from the structure means electron and hole concentrations are related to the potential. So we can write N0 is equal to Ni into e raised to F minus Ei by Kt. That means now it is Ni into e raised to minus Q phi f by Kt. Then we know that the electron or hole concentration at any x is given as N is equal to N0 into e raised to minus Q phi f minus phi by Kt, that is N0 into e raised to Q phi by Kt. So that is the Q phi is this difference, and this N at any point x is depend on Q phi, and similarly holes also P is equal to P0 into e raised to minus Q phi by Kt. So these are the information we will get from this structure. So remember, the threshold for voltage for ideal MOS capacitor is defined as the voltage required to form strong inversion. That means EI below EF by Q phi, the voltage required to make EI bend below EF by Q phi f. That is the strong inversion, and that voltage is called as threshold voltage. And for ideal MOS capacitor, we assign that this work function difference between the semiconductor and metals are same, but actually it is not possible, but practically it is not possible. And we also assign that this insulator, outside layer is the insulator, that is perfectly insulated. That means there is no trapped charge carriers, but in practical case there should be some trapped charge So now we can summarize the mode of operation of MOS capacitor. So first we can see for a p-type substrate, p-type body, when Vg is less than 0, what happened, the accumulation of holes will happen near this SiO2 interface, and that is called accumulation mode of operation. And when Vg less than Vt, Vg is greater than 0 as well as less than Vt, what will happen, this Vg will reject this, repel this holes near this SiO2 interface. That means depletion region formation happens. So that mode is called depletion mode of operation. Then if Vg is greater than Vt, what will happen, it will attract electrons towards this SiO2 interface. So originally it is a p-type substrate, now it is inverted to n-type material, so it is called inversion region. And if it is again we are increasing this Vt, so that time the number of electrons in this region should be equal to number of holes near this region. So that condition is called strong inversion. So we can also define this in terms of Q5S, that is metal semiconductor work function. So we can say that when Q5 is equal to 0, that is the thermal equilibrium condition, that means we have the flat band. And when Q5 is less than 0, that is the accumulation at the surface. So this figure is changes. So this is the first case, we can represent this as the first case, and this is the second case. Q5 is less than 0, this is the second case figure, and Q5 is greater than 0, that is we have electron accumulation at the surface, that is inversion happen. Then Q5 is greater than Q5F, we have the strong inversion, that means surface should be a strongly n-type as the body is p-type. So this is the surface carrier concentration based on this Q5S.